Okay, so this is a highlight talk about Sequre, a new framework with domain-specific language for secure computation. So as mentioned in previous two talks, privacy is critical in genomics. Once we leak genomic information, for example, there's no going back. It remains compromised indefinitely, mainly because we cannot change it. Further, techniques like genotype imputation and properties as linkage disequilibrium render the classical de-identification approaches as insufficient. And these have been breached before in multiple occasions. Still, popular means of preserving privacy today are enclosing data in closed silos with restricted access, which is unsafe, mainly because the genome cannot be changed. Then we have different privacy-enhancing technologies, such as homomorphic encryption and secure multiparty computation, which have strong improvable security, but incur substantial performance overhead, and are also usually much harder to develop than their classical counterparts. Then we have different k-anonymity approaches, which as other de-identification approaches have vulnerable security, and finally differential privacy, which as noted in the paper here by Bonomi and the rest potentially may have limited usability, but listening to previous two talks, I'm not so sure anymore. So we're particularly interested in in solutions that are secure but are slow. And one such example is secure multiparty computation, which in a nutshell enables us to compute on top of private data jointly in a distributed manner, owned by multiple entities, without disclosing any information whatsoever. One way of achieving this is through a so-called secret sharing, in which data is split by each party locally, and then mixed up a bit across multiple computing parties to enable secure computation. As hinted already, drawbacks here are that the algorithms here are usually quite more complex and hard to develop, particularly so for the non-expert users. The performance overheads are substantial, ranging from 50 times to tens of thousands times of slowdowns when compared to classical counterparts, even more so if the network latencies are bigger, because at the end of the day, it's a distributed computing method. And to tackle these drawbacks, we introduced Sequre, which has a domain-specific language with Pythonic syntax, handles all the security aspects automatically, and on the way applies a series of domain-specific optimizations, mostly stemming from the MPC to boost performance. Here's one example. So seemingly simple code, written in high-level Pythonic language, pre-appended with the secure tag, tells compiler to handle the rest automatically. To be more specific, Sequre is actually an end-to-end static ahead-of-time compiler that compiles simple source code, Pythonic source code, to high-performance secure executable on the other end. It does so through a series of different compiling stages, and it's also built on top of Seq language, which is a language for high-performance computational genomics. You could intuitively say that Sequre adds a layer of security on top of Seq language. And the whole pipeline is enabled by Codon, a framework for developing Pythonic domain-specific languages. And here's the example of Sequre in action from before. On the left-hand side, we have the implementation of the householder method implemented in Sequre. And on the right-hand side, we have the same method taken from the existing state-of-the-art MPC application, implemented in C++, and also manually optimized, using the optimizations that otherwise Sequre adds automatically at compile time. So to see what happens under the hood, we will go briefly over a few compile time optimizations. So apart the custom syntax parsing, we have different types of code analysis and transformation, mainly there to enable MPC-specific optimizations. For example, division in the particular MPC flavor that we use, which is additive secret shared-based MPC, is expensive. And it's much better to multiply by 1 over square root than to divide by the square root. And we can search for these patterns at compile time over all the expressions and do the changes accordingly. Similarly, we can tweak the code at compile time to optimize network, and we will see in a bit more detail how so over the following few slides. And lastly, one of the benefits of having a grip over end-to-end compiler is having access to low-level stages of compilation, where we added 2 sets of performance optimizations. In particular, we completely re-implemented matrix and modular arithmetic. So coming back to first the network optimization, we optimize multiplication in particular. Specifically, to multiply 2 numbers, we need to the parties need to collaborate to commute some metadata, the so-called beaver partitions. And the good property about this metadata is that it can be cached per each variable. And even better property is that they can be propagated through operations such as addition and subtraction. So having that said, we can analyze again expressions at compile time, pinpoint the variables for which caching this metadata will result in having a minimum number of the metadata computations in total in the subsequent computation, and hence practically minimize the network overhead when it comes to multiplication. Alternatively, we could scan all the expressions, assemble polynomials, and then just pass the polynomials to pre-optimized secure polynomial evaluation at runtime. However, it depends on the use case on which approach is better. For example, in the example here, computing D times E, for computing D times E, it's easier to just compute 2 partitions for D and E. Applying polynomial optimization here will result in having 3 partitions because I haven't mentioned it. Polynomial evaluation ensures that each input will be partitioned exactly once. The best part is that we can, again, analyze these things at compile time and then count the eventual number of partitions and then decide for the best approach at compile time. And here are some results. This is a comparison of Sequre against the other MPC frameworks across 3 micro benchmarks. The 2 slowdowns are due to the fact that at the time Sequre was using suboptimal solutions for oblivious data structures. And the particular frameworks to take note of here are MPSpeeds, MPyC, and ShareMind, which are most similar to that of Sequre, both in terms of expressiveness and the MPC scheme they use. Finally, we applied Sequre to 3 biomedical applications. First one being genome-wide association study, which is a re-implementation of the existing work, also implemented in a secure manner, secure way, manually optimized and done in C++. Manually optimized meaning that all the optimizations mentioned earlier are added manually to the code. Then we have drug-target interaction inference, also a re-implementation of the existing work, also manually optimized and implemented this in C++. We additionally also implemented it in another library called PySift, which is a library specialized for secure deep learning. And finally, we implemented metagenomic binning, which to our knowledge is done in secure way for the first time here. We took 2 offline algorithms, Gannon and Opal, the first one based on interleaved Bloom filters and the second one on machine learning. Overall, Sequre was up to 4 times faster than the competition. Another measurement that we had is a code reduction against the other code bases, where overall Sequre was up to 7 times more expressive. Additionally, here we added another example. This is taken from the implementation of GVAS above. It's the QR factorization done in Sequre, which otherwise takes about 100 lines of code in the state-of-the-art application. And the best part is that the code that Sequre generates is substantially more efficient, yielding up to 3 times faster runtime. There is no metagenomic binning here because there wasn't a secure code base to compare to. It's implemented for the first time. So to conclude, we presented Sequre, which is easy to use, easy to maintain, the new domain-specific language that guarantees which is less prone to the security leaks and has a high performance, generates a high performance backends. On a final note, I'd like to thank the co-authors of the paper, my advisor Ibrahim Numanagić, Hyunghoon Cho, Berger, and Ariya Shajii. Thank you.